Hi.
Hi, are you sure you can prepare for product based companies through this course?
Yes, sitting at home?
No way!
Yes, way. Don't delay. Enroll now.
Geeks learning together.
Yes.
Hey, what do you mean by a self paced course?
Well, the course material is available in the form of video lectures. And there are multiple practice problems that come along as well. So, you can access all of it anywhere, anytime. And they are available to you for lifetime.
No way!
Oh, yes, way. Don't delay and enroll now.
Geeks learning together.
Hi.
Hi, are you sure this course is just for 2499?
Yes, and you know this is the only course with this expertise across the world.
No way!
Yes, way. Don't delay. Enroll now.
Geeks learning together.
Yeah, so hello everyone. Am I properly audible and visible? Can you please mention the same in the chat box? Yeah, so my screen is my screen visible? And am I properly audible? Okay, you want me to remove the background? Uh, is that not looking good? Okay, let me change. How is this background then? Yes, there is a slight noise of train from the background. Okay. Yeah, so whoever are present, can you please write your name in the chat box to confirm your presence and then we can start very quickly. Yeah, is the background fine now? Like, how is this background better than the previous one? Okay, so good evening, everyone. I welcome you today on the session on binary search trees. And I would request everyone to kindly write their name in the chat box to confirm their presence and so that we can very quickly start. Okay, earlier I was looking like a colossal titan from the Attack on Titan. Okay, now better. Okay, yeah. The whole this is like a home background, so it's kind of looking like very lively as well. Yes, Gotham. Yes, Gautam, it may be possible, but I suppose you won't be very extremely prepared to get very good offers, but in fact, you can get decent offers as well. But if you keep on practicing, you may get a good offer a few years down the line. Yes, thanks for the positive words, Programmer Hub. What's your real name, Programmer Hub? I suppose I am seeing you for the very first time in this session. Is Naikaj here? Aditya, you're from which college, Aditya? Okay, yeah, we have enough people with me right now, so let us begin then. So today will be a session on binary search trees, and in my previous 1, 2, 3, 4, 5 sessions on trees, we discussed most of the theories related to binary trees, and we solved a few problems as well. In fact, not few, we solved around 7 to 8 problems related to traversal techniques, and after that, other BFS and DFS ideas as well. Specifically, in this session, we will be discussing a special type of binary tree called the binary search trees. Okay, so this kind of tree has a very important property of being in a sorted fashion. Okay, okay, is my voice not clear? I suppose it is clear then. Let me do a. Okay, Uttaranchal University. Arun, is my voice clear now? Aditya and Gautam, can you please confirm once that is my voice breaking or it is clear? Okay, it's fine then. Okay. Yeah, so does anyone have any idea about binary search trees or are you hearing it for the very first time? See, there are many people who have joined this session for the very first time, so it seems that you should have a bit of understanding related to binary trees to understand these sessions. Okay, and a general idea about graphs as well. So this session will be actually very easy because I will be mostly discussing about the BSTs, the definitions of BST, and the important properties of BST. Then we will look into problems how to do a binary search on a BST. After that, implementation of seal function, float function, and inserting a node. Okay, so these will be the concepts that will be covered today. And from next session onwards, we will be focusing only on practice because we do not have any much theory left. Okay, yeah, that's better. You should use a headphone. Binary tree with left node smaller than the right node. Yes. In fact, you forgot the root. Yeah, no, I will be using C++ only, not Java. Yeah, in fact, every session is modeled with the language C++ only. Okay, so you can use Java as well, but C++ being the most popular language, we are using C++. And apart from that, let me give you a small introduction about the session. We started this series back in the month of December. So basically, yeah, so in the month of December, we were streaming about graphs, and now we are streaming about trees. And we are coming live daily on Mondays and Tuesdays. So let me write that here. So you will find me on Mondays and on Tuesdays at 10 p.m. Okay, on the GFG practice channel. Okay, yeah. And apart from that, we also have a dynamic programming series going on Thursdays and Fridays. Okay, uh, right here as well. So you can check that out as well. And in fact, everyone who are present here in this stream right now, I would request you all to kindly like the session and subscribe to our channel as well. So basically, we are planning to provide great quality content over the next few months, which would be extremely beneficial for your interview preparations. Okay, so programmer Hub Aditya, so are you comfortable in C++? I suppose you are. Yeah, so let us start then. So the first thing is that the definition of a binary search tree. Okay, so what happens in a binary search tree is that we have a node as usual, and every node will have two child, the left and the right. But the property of the binary search tree is that the value of the node should be greater than the value on the child on the left side, and it should be less than the value of the node on the right side. So the value of the left children should be less than the root, should be less than the right children. So this is how it should be. Okay. In fact, you should give special emphasis on the fact that it is strictly less than and not less than or equal to. Okay. So if you have a tree like this, 2, and the left child is also 2, and the right child is, let's say, 5. Okay. So the right side is satisfying the property of BST, but the left side is not. So we cannot call this a binary search tree. Okay, so this is the property that should be applied to each and every node of the binary search tree. So if it is true for every node, so then we can say that the entire tree is a BST, otherwise not. Okay, so yeah, so I've written a special point here that each subtree should be a BST because, as I said, that this property should be satisfied by each and every node. So it makes sense to say that each subtree, in fact, when you are standing on any given node, whatever is coming below that node is a subtree. So this property should be applicable to each and every subtree. And when you are reaching the very last node, that is a leaf node, which contains only a root and no left and right, so it means that it is in itself a binary search tree. So when you go across all the nodes, this property should be satisfied. If that is so, we call this entire tree to be a BST. Okay. So now all the problems which are modeled around binary search trees are based upon this property only because the data are arranged in this fashion. All the numbers which are less than the root are on the left side, and all the numbers which are greater than the root are on the right side. Okay, so this is how the data is arranged. So this will actually help us solve a lot of problems in which BSTs are applied. So let's look into the first application. Yeah, and one more important fact is that the height of a binary tree is always a logarithm of n. N is the number of nodes base 2. Okay, why am I saying this? Because it may happen that a tree is also skew tree. Okay, in which case the height is also n and the number of nodes are also n. But in binary search tree, it never happens in this way. In fact, all the tree that you will actually get is understood that the height will be of logarithmic nature. So before beginning, I just want to make it clear that because we will be abusing this fact of the height of a binary tree, and the complexity will become log n. Okay, if that is not so, the complexity will become big O of n, which is not the most optimal case. So that is why we must assume, in fact, we must know that our binary search tree, the height of the binary search tree will always be logarithm and not a linear. Oh yeah, yes, you are comfortable with both the languages, but Java, mainly Java, but it should be fine. Yeah, actually, it should be fine. I would recommend you to learn C++ as well. Yeah, Java is also important, but when you are actually using STL of C++, things become very easy. Yeah, hello Nikaj, how are you? Yeah. So this is about the BST, a very small formal introduction about BSTs. Let's look into how to search something in BST. Okay, so we know about various kind of searches like linear search and binary search. In fact, when a data is in sorted order, we usually apply binary search. Now, suppose I tell you, I give you a tree and I ask you to find out whether this node is present in this tree or not. So if you do a level or a traversal or in order traversal, you can do, there are many types of traversal. So you can apply the traversal and check that whether that node is getting encountered or not. But the thing is, the time complexity of such approaches will be big O of n. But we don't want to do that. Okay, we will do that in big O of log n approach. Now this big O of log n approach can only be possible if the tree is a binary search tree. Otherwise, we cannot do in big O of log n. Why? Because we know that our data is always in this fashion that whatever numbers are in the left side will be less than the root, and it will be and the root will be less than the numbers on the right side. So the numbers are arranged in some proper fashion. So we can utilize this fact to find the number, find the node. But if it was not arranged in any fashion like in a normal tree, we have to do level order traversal or in order. So in that case, we have to apply some DFS or BFS. So in that case, the complexity will be big O of n and not big O of h, that is the height. But in case it, since it is a BST, we will do in logarithmic time complexity. Okay, so yeah, so this property is that left is less than the node and less than the right. So value of left is less than the value of node, and in turn the value of node is less than the value of the right node. Okay, so this is about the order. So how we will do that? Can anyone just very simply, in a very brief manner, describe me how can I find the node number 10 in this binary search tree? And tree should be balanced. Yes, it should be balanced. Hmm. Okay, Aditya, you want me to go down slow? Okay, I will now. So, any doubts here, Aditya? So, I told the definition of BST, that how data are arranged in a binary search tree, and in fact, how we can utilize that fact to find some a number which is not which is find a number in the binary search tree. So I give you a binary search tree. The node of this tree is 8, then 5 and 12 are also there. Now I ask you to find a node 10. You have to identify that whether the node 10 is present in this tree or not. Okay, so if you go by the previous sessions and apply level order traversal, in that case, what will happen? You'll go in the first level, which is 8, then 5 and 12, then 4, 7, and 10. So once you come at 10, you know that you have encountered the right answer, so you must return true. But taking this approach in the worst case would be you're traversing across all the nodes. So we don't want that. We want it to be done in logarithmic of n. Because if I give you a tree of 10 to the power 5 nodes, so doing a 10 to the power 5 iteration will take a lot of time. But logarithm of 10 to the power 5 is a very less value. So that can be easily done. In fact, it is around 15. So in 15 iterations, you will know the answer. Okay, we can simply apply iterative approach if key is greater than the root, go right side and less than the left side. Yes, Naika, you are correct. So I suppose everyone can relate this concept to binary search. Okay, so what happens in binary search? We check the middle value, and if the middle value is greater than the value we need, we go to the right side. Actually, then we go to the left side. And if the middle value is less than the value that we need, we go to the right side. What if the number is present more than one time? Okay, yeah, I forgot to tell you this. We are assuming that multiple numbers are not present in the binary search tree. Why it will not be present? I told you that let's say a root is there, so any number should be less than the root to be present on the right side. So let me tell you, I told you we are assuming that multiple values are not allowed in a binary search tree. So if let's say this is 8, and any number which is less than 8 must be present here. Okay, it should be less than 8. So if you are finding any number which is equal to 8, it means that it is not a binary search tree. Okay, so the property of binary search tree doesn't allow to multiple values. Okay, so that is a way, that is basically the use case of this concept. Duplicate is not allowed. Yes, Naika, you are correct. So if duplicate would be allowed, it would not be called a binary search tree. Yeah, since Naika actually told the correct answer, let's look into the implementation of this code. So let me do a dry run. So let's say you're standing on the root of the binary search tree, that is the number 8. Now you want to find the node 10. So you will compare the value of the node 8 to the value of the given node that you need to find. So you see in the first iteration, you observe that 8 is less than 10. So what does this mean? It means that the value which you want to find must lie on the right side, because the value of the node is greater than 8, and you will only find 8 to the right side of the tree. So instead of going searching for the left and then the right, you just directly go to the right. And then you observe that the next node is 12. But now what happens? That 12 is greater than 10. So you know that you must decrease your value. So what you will do? You will go to the right side. In fact, you will go to the left side, because you know that in the left side, the values you will find will be less than 12. So now luckily you find the value 10. Okay, so after you find the value 10, you just return true. And in fact, if it would happen that, let's say, on this case, it was not a value 10, it was 9. So when you are reaching 9, you will try to find the value 10. So 10 is greater than 9, so you will try to go to the right side. But once you go to the right side, you will observe null. So if you are observing null, it means the value which you are trying to find doesn't exist in your binary search tree. So in that case, you will return false. I suppose this is clear, that when we will encounter a null and when we have to return false. Yeah, thank you, Naikaj. So, okay, so let's look into a coding implementation of the same thing. Okay, so what you all can do, Google the question and you will find a GFG practice link. So, search in a binary search tree. Okay, so let me just paste the link of this question on the chat box for you all to follow. Yeah. Meanwhile, I would request everyone who are currently watching me to kindly like the streaming session. Okay, and as well as subscribe to our channel because we are planning to provide great quality content over the next few months. So that will certainly be very helpful to you all. Okay, so yeah, this is the GFG says that it is a very basic problem. Is that so? Is this a basic problem? You can see 58,000 people have solved this problem with an accuracy of 68%. Yeah, so in this input, you see that we got 2. So after that, we have to find the value 87. So we output 1 because 87 is present. And in this case, we want to find the value 11, but 11 is not present. Now you see, in the question, it is already mentioning that your time complexity should be height of the BST and not the and it should not be a linear approach, and you're not supposed to take any space. Okay, so this is how the problem should proceed. Okay, yeah, Naika is basic. Yeah, just imagine 58,000 people have solved this in GFG practice portal. So you see the popularity of this problem. Let's see. Okay, so we got a root. Yeah. So the thing is that if root is not equal to null and root dot value of the root is not equal to the value that is I want. Okay, and in fact, it should be not val. In fact, it should be x because I'm trying to find x. So I will go and if the root see this is a ternary operator. I suppose everyone knows this. So this is equivalent to saying that if let me just write in comment that the if the value of the root is greater than my key value, okay, then go left. Is there a lag in the video? I don't suppose. Maybe yeah, basically there may be a lag because the platform StreamYard actually uses a lot of memory. Okay, so in fact, what I'm writing here is that if the value of the root is greater than the key, then you're supposed to go to the left. Okay, and if not, then right. So this is represented in just a single line in ternary operator. So that is what I meant. So let's submit this problem and check. Okay, so okay, maybe it is root of data. Let's see. In fact, driver code it contains right, left, and data. Okay, this should be data. I really don't know that why the solution is getting. In fact, it's not a solution. It is called search. Yeah. Let's submit this problem and check. Okay, so root data, root left, root data is greater than val. Okay, yeah, again, it should not be val, it should be instead x. Okay, now I suppose everything is correct. Yeah, so you can see that all the test cases have passed, so therefore this question is correct. Okay, so now this was about finding a particular node in my binary search tree. Okay, so let me relate to you the concept of this entire approach to binary search. So what you can do, just relate this approach to the concept of binary search. Then there are two things in binary search called the upper bound and the lower bound. So do you all know about that? Upper and lower bound in binary search. So there is something very similar to upper and lower bound. We can do the same thing in binary search trees also, and we will call that by a very different name. Okay, so this will be our next topic to understand. Okay, so we have successfully see it's how to implement a code that basically searches for a node. Now we will try to find the ceiling of a given node. So let's see. So let's see the you have to find a seal in a binary search tree. Okay, so what is a seal in a binary search tree? Let's see. In fact, you will be given a tree and you will again be given a key value. Okay, so initially we were finding that whether that key value existed or not, but this time we are not supposed to do that. What we will do, we will return the lowest value which is greater than or equal to the value of the key. So for example, in this question, the value of the key is 8. So we'll try to find a node which is having a value greater than or equal to 8. So we see in this example, the value 9 is present. So 9 is greater than 8, and in fact, I will return 9. Okay, so in fact, the value which is greater than 8, greater than or equal to 8, and it should be the lowest amongst there here. So you see 10 is also present which is greater than 8, but we will not return 10, we will return 9 because 9 is the lowest of all the values which are greater than or equal to the given key. So this is equivalent to saying the ceil function in maths or the ceil function in C++ also, if you know about it. Okay, so we have to implement this entire concept in BST. Okay, and in fact, we will utilize the same piece of code we wrote for searching a tree because this is quite similar to searching. Okay, so can anyone briefly describe that how exactly we will look for a seal of a given key in a BST? Yeah, so yeah, so let's try to have a look into the concept then. Okay, so before I go to the code, let me just give you a small piece of dry run approach. So let's say I have to find the value 8. So initially I'm standing on the value 10, which is a root. Now I see that the value 10 is greater than 8. So in fact 10 can be one of the possible answers. Okay, so I'm not saying that 10 will be the right answer, but yes, it will be one of the possible answer. All we have to do is find a number which is less than 10 but greater than or equal to 8. Okay, but since we are just starting on the binary tree, a whole tree is left. So we cannot just assume that 10 will be our answer. So what we do, we have to try to find a value less than 10. So what can we do for a value less than 10? We have to go to the left side of a binary tree, because all the values less than 10 must be on the left side. So once we go to the left side, we encounter the value 5. So once we are encountering the value 5, 5 is basically less than 8. So 5 will not be my answer. So now I want to increase my value. So therefore I will go to the value 6, which is on the right side. So once I come to 6, I realize that 6 is also less than 8. So 6 will also not be my answer. So I want to increase my value. So now I will go to the next value, which is on the left side, because left side is the increased value is present in the left side. So now I encounter 9. So 9 is actually one of the possible answers again, because 9 is greater than or equal to 8. And in fact, it is an actual improvement than the previous answer we knew. The previous answer we knew was 10, but it is an improved version of that. So we will consider 9 now. Now what we will do? We will try to minimize 9. We will try to find that if there exists any number which is less than 9 and greater than equal to 8. So in that case, we will try to go to the left side, because we are trying to find a number less than 9. So once we go to the left side, we see null. So if we are seeing null, it means that the iteration is over, because if you are encountering null, it means just the program is over, and whatever number you are left will be your answer. Okay, so this was about a try run approach of how the algorithm will proceed from the root to the point where you are actually able to get the answer. Okay, so any doubts here? Hello, Arun. You are saying for which question are you saying that with the level order search BFS, so we use queues? No, no, no. It's not a level order search. As I told you that we have to do it in an complexity of big of height of the tree. Okay, so if you are doing with level order traversal, the complexity will become big O of n. Okay, so if it is becoming big O of n, we don't want that. So that is the basically the concept of using binary search trees instead of normal trees, right? You know that the data is arranged in a particular fashion, so you are utilizing that property. While root is not equal to null and root is data. Okay, okay, Gautam, yes, you're correct. Let's see. Okay, so let me just paste Gautam's code. Okay. Hmm, I don't think I can copy this code. Anyway, let's see that. I suppose Gautam is correct. Yeah. Oh, yeah. I've already written the code here in the slide. Okay, so let's see that. Okay. Pardon me for 2 minutes. Let me drink a few water. Yeah, okay. So let us look into the implementation of this code. So basically, what I just described is that we'll proceed as long as we are not able to reach null. So whenever we are reaching null, it means that our iteration is over. So the first step that we will check that whether the value is equal to the key or not. If it is equal to the key, it means that we have got our ceiling function, because I want to find a value which is greater than or equal to key. So if I have found a node which is equal to the key, it means that I have actually found my answer. So in that case, I will just return whatever value I have found. Okay, so this part of the code is that. After that, we will check if the value of the key is greater than the value that we want to find. Okay, so in that case, we will move to the right part, because in the right part we will find lesser values. Okay, because we want to decrease the value. Now, if else, we will go to the we will if it is not, in that case it is also a possible answer. So I will store that value root of data in the variable seal. Initially, I have declared my variable seal to be -1, and my variable seal is actually storing the answer. And then we will move to the left. So this is how it will be implemented. And finally, after when we are reaching null, it means that our iteration is done and we have successfully reached our answer. Okay, so this is about searching a node. In fact, this is seal seal of a binary search tree. Okay, let's see. Yeah, okay, so we have to find a seal. Let's see how we will do that. Yeah, okay, so if the key value of the root is equal to an input, so we can mean that. Let's submit this code and check. But I suppose we will get an error, because in that case we have left, right, and data. Left, right, and data. So this should be data. Okay, and this should also be data. And yeah, okay. Just a minute. Let me check that concept here, and then I'm. Hmm. Okay, as you can see, the problem is of medium accuracy. So, is this supposed to be medium? Like, Okay, there is a compilation error. Yeah, so let's try to implement the concept. Just a minute, find see. Yeah, I cannot able to send my course because this limit cross in comment. Yes, Nika, actually, there is a limitation on the comment which you cannot get. Okay. So as you can see, the all the test cases have passed. So in fact, this code is basically a recursive code, and the code that I wrote in my slide is a basically iterative code. So you can take note of both the codes. Uh, yeah, Nikaj, what you can do, you can type your question in a online ID and try to send me the link. Okay. Yes, Akash Anand is asking for the question link. What you can do, Akash, you can just Google the question. Okay. So and just write GFG practice along with that, so you will get the link. So I've already sent you the link. So at first we did the this concept about how to find the seal of a binary tree, how to actually search for a node in a binary tree, uh, and then we found the seal of a binary tree. So let's now look at how to find the floor of a binary tree. So now the concept is both the same, just a small modification in the code will actually help you get the solution. So the thing is that you have to find a value of a node which is less than or equal to the given value key. So in fact, it is the greatest value that is smaller than the given value equal to smaller than or equal to key. So let's say you have to find a node if the given key value is 7. So what you do, you start with node number 10 which is the root. Okay, so after root, you try to find the value 10, right? So you observe that the value 10 is greater than the value 7. So you are supposed to find a value less than 10, right? So you move to the left part. Okay, so once you move to the left part, you see that you are encountering 5. So now since 5 is less than the given key value, so 5 is a possible answer. But you are not supposed to stop there. You are supposed to find a value which is the greatest of all. So you will try to find the value, you will try to move to the right side because any value which is greater than 5 will be on the right side. So you move to value 6. And finally, once you reach to value 6, that would be finally your final answer because you cannot proceed further from 6. Okay, and left and right of both are 6 and null. So that is the end of the loop. So at the end, you are left with answer number 6. Yes, the iterative code actually I wrote on the slide, and the one I submitted was a recursive code. So I suppose Gautam pasted that code in the chat box. Either you can try using an online ID and send me the link. That should also work. Or you can just try to submit by yourself on the GFG portal. Okay, so this is the concept of float then. Now the code of the float would also be somewhat similar. Okay, yeah. So this is another example for the same concept. Now, in this concept, we are trying to find the value of the node which is less than or equal to 9. So we start with 10, then go to 5, then go to 8. Now, once we reach 8, 8 is a possible answer. So we will try to increase 8. So we go to the right side, but we reach null. So whenever we are reaching null, we are terminating our iteration, and the last value that we have encountered is our answer. So answer is also reached. So this is how the floor function will be implemented, and this is an iterative code for the same. Okay, so first you write a while loop, and the condition is that it should not be null. So you check the value. If it is equal to key, it means that you have actually found the right answer. So you return the right answer. But if the key is greater than the value, then you move to the right side, or else you move to the left side. And if the key is greater than the value, then it is also a possible answer. Okay, because you want to find a value which is less than or equal to the given key. So this is how the iterative code will look like, but a similar code for recursion is also there for finding the floor. And seal and floor both are same thing, just you have to change one less than sign and greater than sign. It is just exactly the same. Okay, so I can try to submit the floor function as well. Floor of a binary search tree. Okay, yeah, I opened the article link.